This is what's called a multi-segment LED display. Should be able to see it forms the digit 8 with a little decimal point. So it's called a 7-segment display. 2 vertical ones on the top, 2 vertical ones on the bottom, and then 3 horizontal ones at the top, middle, and bottom. And then it's actually 8 because it has a decimal point, but it doesn't have to. The 7-segment display optionally has an 8th, but this one has 8. Now, I got this device in a kit, just a bunch of other components. And I'm sure that there's manuals and spec sheets online for the company that made it. And for the more complex of their stuff, like the integrated circuits, I will of course be looking at that, because one does not simply poke and prod and figure out how an IC works. But this is the kind of thing that's actually instructive to try and figure out how it works. First of all, we can make one assumption, that it works similarly to a common cathode or common anode LED. Remember the RGB LED where it had 3 pins, 1 for each color, and then 1 that went to the negative terminal? So there's 8 LEDs, 7 for the digit, 1 for the decimal point. There are 10 pins. There are more pins than there are even LEDs. There's not double, so they don't each have their own individual path, but they wouldn't need it. In fact, if we have 8 components, 8 LEDs inside here, we'd only need 9 pins. We have 10. We have more than we strictly need. So why don't we just poke and prod and see how it works? So I have here my multimeter, and I'm going to use something called the continuity and diode test mode. Not every multimeter will have this mode, and the ones that do, not every one of them will be suited for LEDs. Some of them will work with only the normal diodes that take 0.3, 0.7 volts kind of thing. LEDs typically take 1.5 to 3.5 or so. But this one, I have found out, does indeed work just fine with LEDs. So I turn that mode on. If we have essentially a short circuit or the next thing to it, then you will hear a tone. And if you are powering an LED with it, for example, this one, and if you put the positive terminal into the positive side, the negative into the negative, it will not beep, but it will very dimly light up. So you can use that to very briefly and safely test your diodes if your multimeter supports it. So basically what I'm going to do is assume this 8-segment display, this 7-segment with a decimal point technically, is a common cathode or common anode LED array. That should be a bit easier to see as long as it doesn't fall on the floor. So what I will do is we'll say, okay, I will take the positive lead of my multimeter and I will stick it in one of the pins. You cannot obviously check every combination of pins like this because it's 10 factorial. So you're going to need to be intelligent about it, but we can do 10 at a time. So the positive I'm going to leave in one spot. The negative I'm going to put in the other 9. Now if we put it in the one that one's in, we obviously get a tone because it's short-circuiting to itself. But how about the other 9? So let's say pin 2, 3, aha! So we see that pin 3 just lit up. All right, it's lighting up the middle segment. I hope you can see that. If you can't, take my word for it. But it lit up one segment of the LED on pin 3. So positive is in pin 1, as I'm numbering them, and negative is in pin 3, and that lights up. 4, 5, 6, 7, 8, aha! When I put it in pin 8, it also lights up the same segment, 9 and 10. So pin 1 is in the top left corner, pin 3 is in the top middle, pin 8 is in the bottom middle. Now remember, we had 10 pins. We have 8 LEDs. So that's 1 pin for each LED is 8. Then one common cathode or anode would be 9 pins. We have 10. What if there's just 2 pins short-circuited to each other so you can connect to the top or bottom? Well, that would certainly fit what we've seen. Now what if I do it in reverse? Instead of the positive terminal in pin 1, I'm going to put the negative terminal in pin 1. And then we'll try all the other pins. 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, take my word for it, none of them lit up. Not a single one. So, obviously, we have figured out the direction of our diodes. Positive in pin 1, negative in pin 3 or 8 means that this is a common cathode LED array. Cathode is the negative terminal. Let's confirm that. So I'm going to leave it in pin 3 this time. I'm going to move the positive terminal from pin 1 to pin 2. A different segment lights up. Pin 4, 5, 6, 7, 9, 10. I'm sorry, my hand was blocking it. I can do only so much. Every one of those 8 combinations lit up a different segment. What about our extra pin? Pin 8. A tone. That means between pin 3 and pin 8 is a short circuit. So we have here 8 LEDs common cathode and 2 pins shorted together that both work as the common cathode, whichever you happen to desire to use. So why don't I show you how this is wired up? So we have 2, 3 like this, 2 like this, and 2 like this. So you can see that can be a 1, a 5, an 8. That's how it works. And then our decimal point. So we have 8 LEDs. So somewhere in the device, beneath the cover on the front, is an LED in each of these 8 spots. So let's lay out some LEDs. 1, 2, 3, 4, 5, 6, 7, 8. So here is our device, which remember has 10 pins. So I have the positive signs, the anodes, out here. This is where you connect your signal pins. And it's not going to be like this on a device that has many, many more LEDs than this. It's ridiculous to think about how many wires that is. That's where you use shift registers and such. But for something like this, if you're using a single-digit display, it's not unreasonable. And you could always connect a shift register to this. Just because it doesn't have any sort of switching in itself, you can connect it to a switcher and only use a few data pins. But the point is, it has these pins. But what about the other 2? There's 2 more pins here. Well, remember, these are the common cathode points. Remember how this is short-circuited to itself? It's like that. It just goes through. And then this connects here, 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 and, not to least, here. So you've got 8 pins for 8 LEDs that are connected to the positive ends, the anodes of those LEDs, where you supply the voltage, either on or off, to say whether the LED is on or off. You could dim them, but you could also use PWM. That's what you would probably use, because you're going to connect this to a microcontroller. There's not going to be any manual situation to control the segments of a digit. This is going to be done by a microcontroller, or at least by some sort of mechanical monstrosity of clockwork that works this way anyway. It'll just be a mechanical microcontroller. And then all of the negative terminals connect to these 2 shorted pins, and that is where you put your negative power. Your negative terminal, your ground, your cathode connection. And it's that simple. The others are your data signals, and you just connect those to your chip. And you don't have to have both of these. One will do. You can have both of them connected if you want. Not really any reason to, but if you had some sort of device that was putting a lot of current through this, and if it supported a lot of current without exploding, then having 2 connections instead of 1 gives the current 2 paths to follow, which means half the current will follow each. You can always split current that way by adding more wires and more resistors and more whatever. If you need a lot of current to flow through a very weak diode, then just add more diodes in parallel, and they'll each split the current with the same voltage drop, roughly. Again, as we just demonstrated in the previous video, the lowest one will take it, but if they're all very, very, very close, it will have the effect you want of splitting the current, because at least some of them will be on, and the others will probably be on in trickle mode. So it's a lot of lines, but it's incredibly simple, isn't it? And you can almost see why it's hooked up this way. It was difficult to see when I was doing it there, but the 4 up here connected to the top 4 segments. These 4, the ones down here connected to the remaining 3 and the decimal point. So it's physically on one side and the other. So this is also a rough physical representation of how it's structured inside. And we figured this out without ever finding a spec sheet. And again, you cannot do this with more advanced circuitry. If you're dealing with a full-on integrated circuit, you can feel free to poke it and prod it all you want. Hopefully you don't fry it before you go and find the spec sheet. But for simpler stuff like this, it can be fun. And now that we've deduced this, we could make our own. It would be more expensive and bigger, but let's say you wanted to have a bunch of flashing lights or indicators or whatever on your robot. Well, now you know how to wire it up. Nice and easy. You know, have the ones on the back of the robot and the ones on the front of the robot have a wire connected in the middle that connects to your negative terminal of your battery for the robot. And we're not even violating any patents. So while you go and get your soldering iron, I'll be seeing you.